All right, let's roll. So we're finally to the end of this playlist. I finally have it all working. So basically, the functionality that was in the previous playlist is now in this playlist, but now we're using OpenGL rather than Canvas. Well, WebGL. We're using WebGL 2 specifically. So let's give this a shot. Show you what we got here. So here's starting up. All right, we're going to go into render mode 1. Render mode 1 means that we don't use the default shader, but defer the shader routine to whatever editor is in focus. This is just the shader for the master editor. So when no sub editor is in focus, we just have this little pattern, right? No big deal. Okay, I'm going to press tilde, and when I press tilde, that says that the master editor will intercept whatever command comes next. So the master editor decides what other editors are going to get the commands. I don't want the master editor to intercept too much stuff because then it limits the options of what the other editors can listen for. Therefore, I've decided if you want to give the master editor input, you always have to press tilde first. So I'm going to press tilde and I'm going to press 1. So now editor number 1 is in focus, and editor 1 is my testbed shaders editor. What you're seeing here is the memory view of our TAU. What was that for? Tiles as uniforms. I think that's what TAU stands for. Let me check my notes really quick. TAU means, and if I don't have that in the notes, texture as uniform. My bad. This over here is just a view of the different pixels that are encoding uniform values. The black and white you're seeing up here, that corresponds to, let's see if we can find this really quick. TAU, we'll go 001 dash, okay, find next. Okay, so I made a little helpful grid here. I don't know if I have shown that off before, but here are our different uniforms that are encoded into the texture. I've made them all linear because I'm done debugging, and I can easily see that there's no collisions here, because if there's collisions, oh boy, you get weird stuff. You might as well be coding in C with the weird stuff that'll happen if you make your data collide. Basically, you'll memory stomp yourself if any of these values are the same. Okay, so let's, within editor number 1, let's press the number 1 on the keyboard. And here's just a shader that I did, and I put it into slot number 1 in the testbed shaders gallery. And then if I press number 2, oh, hey, look at that. We got a little Mandelbrot. That's cool. And I got the zooming in and out to work with the camera. So I'm going to press plus, and we're just going to zoom in. Now, we're not going to be able to zoom in too much because we're using an inclusive rectangle and just changing the size of the selection area in order to zoom in. So at most, the maximum zoom will be when we have exactly 1 pixel selected, and then we can't go any deeper than that. So I think we can only go about this deep. Oh, I guess a little bit deeper than I thought. And then now you see that we're coming back out the other way. So I'm still zooming in, but it's zooming out because the rectangle has crossed over itself. The rectangle is like flipped, right? The left edge went over the right edge, and the top edge went over the bottom edge. They've crisscrossed because I'm using the unsafe rectangle manipulation code right now in the camera controls because I wanted to see what it would look like if I did not add any special bounding logic. Now you'll notice that, this shader isn't like too fancy. It's not like, oh my god, it's amazing. This was just, I needed some shader to just throw into the code where I could test zooming. And though this shader that I did can test zooming, it doesn't give you as much feedback as the other one. So if I press the number 3 within editor 1, we have these other shaders, and they're just blank spots, right? Just flashes of color, right? So we get all these numbers. So all the way up to 9 is just flashes of color. And then eventually, as we want to prototype other shader code and we need a place to put it, we have a place to put it, which is awesome. So I'm going to press tilde and then 2. Okay, now we are in editor number 2, which is going to be our tile map editor or tile set editor. Probably tile set first before a tile map, so this will probably be the tile set editor. And then from there, I'll have, like, editor 3 will be a tile map editor, and then editor 4 will probably be a world map editor, where you stitch together multiple worlds. So let's hit plus and minus. And so we're zoomed out, and zooming in, zooming out, zooming in. Now if we press the arrow keys, now see that change in color? That's actually us moving, right? Now it can be kind of hard to see that you're moving because the editor is snapping when it moves from one place to the other. And that's actually by design, right? So the editor always moves exactly one camera over when you press the arrow keys. And there's no animation. And the reason for that is eventually we might abstract this, and we might not want the user to know that they're in this huge data set. Like, we might want to only be zoomed in on a few tiles like this, and like maybe this is like an auto tile set with 16 tiles, right? Like your standard auto tile set where it has the 4 bits for the touching values of if it's touching the bottom, top, left, or right. So maybe we want this to be a tile set, and then we want to like flip to the next tile set by just, pressing up and down and getting all these different tile sets. So one of the reasons for why all of this is colored here is just to demonstrate that within the shader code, I was able to get internal coordinates on every single tile. So every one of these colors you see is actually a pixel value. And the pixel value will be used to, encode the tile information. Like what kind of tile it is will just be a uint32 value. We might abstract that information in some more creative ways, but right now you could consider what we're looking at as like a raw data view of tile map data. You'll also notice that there's that gray up here, and this weird color right here, that's just for me debugging, right? I can draw debug patterns to the data and then make sure that I can see those debug patterns in the shader code to confirm that my shader is actually looking at what I think it is looking at. And so I wanted to make absolutely sure that I was not off by 1. Therefore, I changed only 1 pixel right here on the data. There is one more thing. This data set I'm looking at is just 512 by 512 pixels, and it is on the master memory, which is 2048 by 2048 pixels. So we've subdivided the master memory into 16 subsections, which I am calling memory cells. The memory cells are indexed 0 to 15 inclusive. There is another concept called hot swapping indexes, which are 1 indexed and go from 1 to 16, and they directly correspond to the memory cells. So I can, if I press the different digits on my keyboard, I can set the hot swapping index to different areas on the map. So, oh, wait, my bad. It was something else. Oh, so it was not the number keys, because obviously there's 16 unique numbers I would need. So what I used instead of the numbers was XY navigation on the memory cells. So I'm going to press the, so I'm using WASD. If I go left, you'll notice that, right, that goes away. And it looks kind of like we're just navigating like normal. But actually, we're going to a completely new data set. So you can kind of see that there's this edge around here. And if I move over, you'll see how the gradient changes, right? Because we're totally in completely different data sets. And so there's 16 different giant chunks that are 512 by 512 that I'm navigating through right now. And you'll see that this one has something weird in that corner up there. What could that be? Let's go zoom in. Oh, hold on. Huh, that looks kind of familiar. Doesn't that look familiar? Let's go to editor number 1 really quick. Editor number 1, and we'll go into shader slot 0 in editor number 1. Oh, wait, hold on. Editor 1, shader slot 0. Oh, hey, look, that looks kind of familiar. Let's zoom out here. So we kind of screwed up where we were. But if you look, you can tell that this right here is a sample of pixels where we are encoding those uniform values, right? And if we go over to editor number 2 again, right? Doesn't that look kind of familiar? So here's the view in editor 1, and here's the view in editor 2. So you see how we're just taking those pixel values, and we are just drawing them with a little shade. And the purpose of this shade isn't to like make it fancy and graphical. The only reason for this is just to prove that we were able to get the internal coordinates of every single tile. Because if we want to do something fancy, like let's say we want to get a sprite sheet and we want to blit hand-drawn, sprite art onto different tile values, we're going to need to be able to calculate these internal coordinates within every single tile, right? So green, right? So this is all green. Okay, so green might map to, a grass tile, right? So then we pull up the grass tile image, and then we copy all of the pixels from the grass tile image into this tile. And seeing that we were able to properly calculate gradients in these tiles, we know that we have all of that information, and we were able to manipulate it to our needs. And so abstracting the gradient mapping logic to something like bitmap mapping will be really dead simple. Like the hard work has already been done. It's just now taking that hard work and abstracting it into something more useful, right? So the hard math logic, that's already been done. It's just some of the abstractions need to be done now. So let's find where that shader logic is. So how could we find that in this huge file? Okay, well, here is editor number 2 variables. So we're trying to keep with something really simple. Write these very long tokens, but they all have a very specific name. Naming conventions, it is better to have consistent names and consistent conventions than to have a good memory. Because, man, you'll just code so much stuff. You're eventually going to forget it. You need to be consistent. So this is texture as uniform set number 1. And these are the constants for editor number 2. And we have the tile exponent, the tile span, the camera position tile X, camera position tile Y, the hot swapping index that we'll use to render, and then this use HYP variable, which honestly I'm not going to tell you what that does. And it's not that I don't know what it does, it's that we're getting to the point where I've done most of the groundwork I need to do, and pretty soon I'm going to stop recording. Because we're getting to the point where there are some ideas I have for how I'm going to actually do more of the specifics of rendering that I find might be highly patentable. So there's some things that I'm not going to explain. I don't know if I'm going to keep on recording more videos or if I'm just going to stop altogether. Because I could keep on recording things but then leave things out. If they're related to some of the tech I'm working on, but I don't know. I'll think about it. So now that we have these variables, we can grab onto them and kind of find them referenced in the code. So right here, these editor variables have been injected into our shader code, right? So the actual index position where this data is stored is now being injected into the shader code, and that's how we're going to be able to locate these different pixel positions, we're locating them by index. So 0 is here, 1 is here, 2 is here, 3, etc. And then we scan like this. And the reason we're using index instead of XY is because then you can easily serialize it and do it in a predictable, easy to manage order. So if we go back here, right, like we can, well, hold on. So if we go back here, you can see how we have these all in just a nice linear order. If we were somehow encoding this with XY instead of just an index, that would be a much harder challenge. And I think I didn't show the screen when I did this, but so those values you saw that are all in index order, right? This is 0, this is 1, this is 2, and then you keep counting this way. Once you get to this edge here, you go down and you read just right to left, right? Right to left, like you're reading a book, and that's the index order of all of these tiles that are being stored. Now you see that there's a little, the red and green here. This data was filled with like a default pattern before we put anything meaningful in it. So instead of 0 initializing the data, we initialized it with kind of like bogus patterns that we could use to like be able to inspect the data visually and see if we know where we are and stuff. Okay, so let's go. How much time do we got? 16 minutes, so we haven't gone over yet. Let's take this variable and let's hunt it down some more. So we found it in the oh, we're going backwards. Let's not go. Well, we're already here, so I guess. So more getters and setters, right? And this looks like a whole bunch of code. It's not. This is basically a cut and paste job. You'll notice this code is written horribly, right? Right? Well, why would you look at the indentation in here? Well, why would I do that? Why is this written such crap? Why is this crappity crap? Well, the point is that if you look for the delta in the code, it's all right there, vertically aligned, right? So all you gotta do is cut, paste, and then type something different, right? Column select, type something different. Column select, type something different. Right, because we have so much redundancy here, we're not going to worry about, oh god, it's so hard to read, right? Oh my god, we're not going to figure it out, right? Because you look at this bizarre logic once, pull your hair out maybe, get pissed off at how stupidly formatted it is, but you look at it once and then you should assume, because of the uniformity of all of this, that all of it is the same, right? It's the exact same structure for every single one of these. And the only thing different is the part that matters is the part that we made most obvious, right? So we sacrificed some of the formatting to make it absolutely obvious where the deltas were in this code. And you might say, wow, that's a lot of redundancy. Like, well, that takes up so much space. Why don't you make some type of like useful utility that could do this for us? And no, I think this was the best way to do it. Especially because I do want to be able to easily move this into C code. So I don't want to do any like fancy things, and also if we add another layer of abstraction, that'll just make the logic harder to follow. Like, this is ugly as hell, but everything is nicely exposed, and you can see how everything works. So I'm going to keep it that way. I kind of explained how it works before, but I might as well go into it again. Okay, so, right, we have a putter and a getter, so let me just highlight those for you. So here's our putter, and here's our getter, and these are all pertaining to editor number 2, right? Okay, so let's clear that. So what we're going to do is we're going to take our global classes, and we have a texture as uniform set number 1 container, which has a uniform put command, right? It has a uniform put, and you better bet that if there's a uniform put, there is probably a uniform get with a very similar, consistent name, right? So when you use uniform put, we're going to go into our global configuration, and we're going to find those hard-coded index positions of where the data is stored on the texture, right? And what else do we need in order to, I guess, pixelize or quote-unquote serialize the data? Well, we need the actual value, right? So this is the physical location of the data, and this is the actual data we want to persist, right? And then for the getter, You only need the actual position of the data that you want to get, right? Okay, so what's next? How much time we got? Okay, we're at 19 minutes. We can keep on going. So, well, we're going backwards already. Well, whatever. Let's see. Tile exponent. Control F. Okay, let's keep on going, see where we end up. Okay, static hack. Okay, so obviously, long, obnoxious name. That means, for whatever reason, there was something awkward and non-uniform in my code, and I just want to make it kind of blatant that this sucks and it's ugly. So what we have here is using the POW function in a shader. Doesn't work too well with integers because you have to take the integer, cast it to float, do power, and then cast it back to an integer, and that's a lot of unnecessary work when we could just pre-calculate things. Therefore, even though I do have this tile exponent value available in the shader, we're going to also pre-calculate the tile span. So right, and this is the formula, right? So you take the exponent, you take 2 to the power of the exponent, and gives you the number of pixels in a tile. And so different tile exponent values are basically like these different zoom levels, you could think of it as. Anyways, when we want to put the tile exponent, we also want to remember to calculate the tile span, and then we want to cache both of those. So this is a little wrapper code for that. This is written statically, and then this right here is written as a member function, right? Because we have editor2. So this is like calling editor2 dot this function here. Now you'll be like, well, why didn't we? That's weird, because why is it this big long thing then if it's a member function? Well, we're using a object-oriented procedural style. So we're writing OOP code as if we were doing it in C, if that makes sense. And in C, this argument is always the first argument, right? And so my namespace, AA2 is my namespace. I make my namespace lowercase letters when the function is supposed to be private. The next thing is the object that is the target of the function. So this is editor02. So that's the this of this function. So it's a member function of editor2. And then the actual function name is this part right here. So put tile exponent and tile span. So lately I've been favoring more of just keeping functions very, initially I wanted camel case for functions and then underscores for variable names, but to make it easy to find things, so example, if I go like this, right, and I do token highlighting, boom, find everything. Now, if I wrote that in camel case, I would not be able to easily see all those connections. They wouldn't light up like that, right? So camel case is still what I want to use for functions, but when the function name is referencing a specific variable, I'm going to write the variable as it is written everywhere else in the code, even if it appears in a function, right? So what else? What are we at? We're at 23. So there's some logic. I'm not going to go over all that. Let's just go find more places where tile exponent is referenced. So we have next tile exponent function that just increases the tile exponent and then clamps it between 0 and 8 inclusive, because those are the tile exponents that I am supporting for reasons that I won't get into. Has to do with the layout of the data and what the data will support. So I am using, I don't know if it's obvious, but there's a lot of waterfall going on here where I've had some of these ideas for like 5 years and I'm like putting them all together. So there's a little bit of Scrum, a little bit of waterfall, but this is not a completely Scrum operation. I think that, having a clear idea of where you want to go is a good idea. So anyways, let's keep on looking for different references to tile exponent, because eventually we will get into the actual shader code. So what are we looking here? So they were calculating the rectangle bounds, and then looks like checking to make sure that the camera is within those bounds, I'm guessing. Camera less than the x0. Oh, no, this is definitely outside of bounds. Yep, and then there's error for out. Oh, sorry, you can't see that. There's error for out of bounds. So this is checking to see if out of bounds. What else? Okay, yeah, so this is, okay, move any cam txy. So this is a little helper function for moving the camera tx and camera ty position on the editor. So it is a member function, so the first argument is the self argument, and then we have the offset x and the offset y. So we got the camera tile position here, and you'll notice that I have GP here, and I did that intentionally for get put so that I can remember that we got a persisted at the end. So right, we have to, this is kind of like, this is almost like an SQL query in abstraction, where we have to get that data out of our pixel buffer, and then we got to do some manipulations with it, and then we got to make sure that we put it back. So we got to get it, and then we got to put it back after we're done doing whatever we're doing with it. So one of the things I did is I have a rectangle bounds object. So this function here has a side effect, which is to change the rectangle bounds here. And you'll be like, well, that's bad code with the side effect. Well, you know what? The thing is I don't care. That, and I don't want to be creating complex objects on the fly and destroying them all the time. So if it's a struct or a class, no creating and destroying on the fly. You better have a really good reason for why you're doing it, because otherwise you're just asking for memory leaks, you know? And I would rather have a side effect than needlessly create and destroy something. You're gonna, if it's a managed language, you're abusing the garbage collector. If it's a managed language, a garbage collected language, right? You're abusing the garbage collector. And if it's not a managed language, you're just opening yourself up for another place where a memory leak could happen. So the best way to avoid memory leaks is to not malloc and free. I'm not saying never do it, but limit yourself to where you're doing it. Only do it where you really absolutely need it. And you'd be surprised at how many places that you do not need dynamic memory, where you think you need dynamic memory because you're spoiled and overuse the feature. No, really. Okay. So this might look a little bit overly complicated, right? So we have the offset x and the offset y, and we're going to get an absolute value of these, right? And we're going to call them the U32 offset x and the U32 offset y. Well, the reason for that is these values are actually stored in pixels, and all the pixels are just a series of bytes, right, encoded into a uint32. Well, technically not on the GPU, right? It's actually stored as all separate bytes, but when it's on the I like to think of every single pixel as a uint32, so I think of it as 4 bytes clustered together. Either way, it's going to be unsigned. So we have these utility functions for adding, add, subtracting, and making sure that when we add and subtract that there is a clamp applied. So this might look like a lot of work just to add and subtract, but the point is that if right now there's no such thing as like unsigned integer in JavaScript that I am aware of, right? Because it's all loosey-goosey with the types. But if we want to move over to some C code later, we're gonna have to make sure that we don't. If the function needs to use unsigned integers, we're gonna have to use unsigned integers. Right? So we get the absolute value, and then we compare with the signed value to determine, okay, well, are you positive or are you negative? And if you're positive, we'll just do the add function, and if you're negative, we'll do the subtract function. So I'm not going to do any weird shit where it's like add command, but adding a negative number. None of that. But yeah, that's whatever. I need to just keep on going. So I'm going to stop recording, and then we'll get to maybe the shader code. I don't know. We'll just keep going.